Students, now we learn the module 5. Module 5. Now, in module 5, there are mainly two topics, namely the joint probability distribution and the sampling theory. First, we concentrate on joint probability distribution. Now, what is this joint probability distribution? It is nothing but distribution of two variables. So, the we have studied the two kinds of variables, namely the discrete variable and continuous variable. First, and in this for you, the syllabus they include only discrete joint probability distribution. That means you are studying only the joint probability distribution of two discrete variables. Okay, to understand this, let us consider a simple example. Let's consider students in a class. Let's consider there are 100 students in a class. Out of this 100 students, there are 70 boys and 30 girls. Now, out of the 70 boys, so 40 boys are wearing spectacles, whereas 30 boys are not wearing specs. Out of 30 girls, 20 are wearing specs and 10 are not wearing specs. Now, if you want to find out what is the probability that a student selected at random is a boy, then the probability is very simple. P of B is nothing but 70 by 100, 0.7. Similarly, you can find out probability that student is a girl, which is nothing but 0.3. Probability of G equals 0.3. It is also simple. But let us consider this situation where we all selected a student. A student is a boy and wearing specs. A student is a girl and not wearing specs. Student is a boy not wearing specs. Student is a girl wearing specs. How to find this probability? That probability can be found at joint probability distribution. That means here we get a joint probability distribution where the two variables, one is the gender of the student, boy or girl. That variable you can call it as X, boy, girl. Other is variability of specs, that we can call it as Y, whether this student wears specs, not wearing specs. Okay, let's consider data in this form of the table. So how many boys wearing specs? There are 40 students wearing specs, 40 boys. And how many not wearing specs? 30. Similarly, how many girls wearing specs? 20. Whereas 10 are not wearing specs. And total number of boys is 70. Whereas total number of girls is 30. Now, how many students totally wearing specs? 60. Combination of both boys and girls wearing specs. How many students not wearing specs? 40. Okay. Now, the total number is nothing but this 100. Whether you take this sum or this sum, it's always equal to, they are same. In this case, it is equal to 100. Now, we write the required probability in the form of a table like this. X, Y, where Y takes the value, yes, two states, wearing specs, not wearing specs. X takes two value, either student is a boy or a girl. Now, to find the probability that student wearing specs, A boy wearing specs is nothing but 40 by 100. How much? Zero point 0.4. A boy not wearing specs is 30 by 100. Zero point 0.3. A girl wearing specs, zero point 0.2. That is 20 by 100. A girl not wearing specs, boy student is a girl and not wearing specs, zero point 0.1. Therefore, so this gives the probability that student is a boy and wearing specs, but this gives the student the probability that student is a girl and not wearing specs. Like similarly, this gives probability that a student is a girl and wearing specs, whereas this is the thing but probably the student is a boy and not wearing specs. Okay, so this is called as joint probability distribution. Now, to get a general one, we just extend this x1, x2 to xn, and we extend this as n y1, y2, yn. So, the simple example, I've taken two variables such that they take only two values each. Only two states here, wearing specs, not wearing specs, only two kinds of genders. Okay, so we can also come up with examples where the x can take more values, more than two, and also y can take more than values, m number of values or n number of values, ym. And this is given by the probability density function PDF, which is denoted as P of xi comma yj, or in simple notation P suffix I j. Exactly. A joint probability distribution is in the form of a table called probability contingency table. It's like this: x, y, where x takes the values x1, x2, etc., xn. Y take the values y1, y2, etc., ym. So n can take some positive integer, m also can take some positive integer values. They may be same or they may be different. Okay, that depends upon the nature of the variables. Now, in this portion of the table, we write probability values. This is P11. The P11 is probably that x taking the value x1, y taking the value y1. This is probability suffix 1, 2. This is probability 1m. Similarly, this is probability 2, 1. Probability P22. This is P2m. And here it is Pn1, Pn2, Pnm. In general, P suffix I comma j equals probability that x taking the value xi, y taking the value yj. It's also written as probability of xi comma yj, or f of, in some books they use this notation, xi comma yj. So this is the PDF, probability density function of joint part distribution, and it satisfies the two conditions that it takes only non-negative value p of I j is greater than or equal to 0, and second condition is sum of all these values must be equal to 1, that is double summation I ranging from 1 to n, j ranging from 1 to m, Pij is always equal to 1, and these are the two conditions satisfied by that function called PDF, and the corresponding distribution is nothing but discrete joint probability distribution. One example I given here. In fact, I started with an example only. Okay, fine. Now, so can we find individual distribution from this? That means the distribution only for variable corresponding variable x, correspond to variable y. They are called as marginal distributions or individual distributions of x and y. So we already know the values taken by x here. So if we just find what is the p of x1, p of x2, etc., p of xn, then if you take those probability values along with these values x1, x2, etc., xn, you are getting probability distribution of the variable x. Similarly, along with these values of y1, y2, y3, etc., yn, we have to find what is the probability of y1, probability of y2, etc., probability of ym. So if you take those two set of values, then you get probability distribution of y. It is easy to get those marginal distributions. They're called as marginal distribution or individual distribution of x and y. Now let us define them. So marginal distributions of x and y. So we already know the values taken by the variables. Just we have to find out the probability of those values taken by the variables. Now to get probability of x1, just add these probability values. To get p of x2, add this sum of this probability value. Similarly, to get p of xn, add this. So in general, define capital Pi, or you can use some other notation for that. P of xi as summation Pij, where I is fixed. For P of x1, x is 1. For P of x2, x is 2. So there is I is fixed. Okay. For a fixed I. J takes the value from 1 to m. Or in simple words, just take the sum of the entries in the ith column. First ith row. First row means this one. Second row means this one. Similarly, ith row. Okay. Then these you find for all values of I. For all I equals 1, 2, 3, etc. And then this distribution x p of x, where x takes the value x1, x2, x3, etc. xn, p of x1 or p1, p of x2, p of x3, p of xn. This is called as marginal distribution of x. Marginal distribution of x. Okay. So, or instead of marginal, you can call it as the distribution of x or separate distribution of x. In the same way, you can find out marginal distribution of y. Now, just we have to consider the sum of these values. Some of the values in this columns, entries in this columns. This one has probability of y1, this is probability of y2, etc. Probability of ym. It's in general. So let us define this as p of j bar, capital P of j bar, same as p of yj, which equals to summation Pij. Now we have to fix j for fixed j. For fixed j. Now you take the values I. We all know the values I ranging from 1 to n for all values of j. That means first you have to take, so some of the entries in the first column, then second column, third column, etc. nth column, mth column, mth column. Then that set of probability values along with the values of y will give you marginal distribution of y. Okay, which is y1, y takes the value y2, etc. ym p of y1 or p1 bar, other notation, j equals 1, p of y2, p of ym. This is marginal distribution of y. Now, can we find the, now that means we have got individual distribution of x and y from this joint probability distribution. Now, other way, can we find this joint probability distribution from that individual distribution, this individual distribution of x and y? So it's not possible always. Getting individual distribution from joint is possible always, but from joint probability distribution, you can always find marginal distributions. It's always possible. But the other way, this is possible only under certain condition. That is, from marginal distribution you can find joint probability distribution. The condition is the variables has to be independent. Now we define what is what is the condition for the variables to be independent. The variables x and y are said to be stochastically independent. Stochastically independent or simply independent if this condition is satisfied. That is, p suffix ij equals probability of xi into probability of yj. That is same as the other notation for this is capital Pi. Other notation for this is Pj bar. And what is the other notation for this? P of xi comma yj. If this is satisfied for all values of x and y, then we can say that they are stochastically independent. In that case, we can find the joint probability distribution from the marginal distribution. This condition is very easy to understand. If you consider this probability contingency table, so this value must be equal to product of sum of the entries in this row into sum of the entries in this column. If in general, probability of any element, that's Pij, but product of sum of the entries in ith row and jth column. Okay, so while working problems, we can find out them very easily. That condition we can check it for very easily. Okay, next thing is, now can we find relation between these two variables, the two variables x and y in a joint probability distribution? Okay, so in statistics also, in the module 3 you are studying the correlation and also covariance. You're also finding them relation between these two variables, namely covariance between these two variables, how they are changing. Those two variables are changing. Okay, so it is the thing what covariance. So it is nothing but, it is denoted by the notation COV of x comma y, and we can show that it is nothing but equal to expectation of x into y minus mu x into mu y. Mu x into mu y. And what are this notation stands for? This is nothing but mean of the distribution corresponding to variable x. This is the mean of the distribution corresponding to y. This is the thing but expectation of xy in the what is called the joint plot distribution, and that E of xy is nothing but double summation I then j. So Pij into xi or you can write xy yj first into Pij. So this double summation value give you e of xy. Now correlation between these two variables is correlation coefficient. That also you're studying in the statistics. Okay, correlate will explain the how these variables are changing. What is the exact correlation is given by some constant which is between -1 and +1, and that correlation coefficient is, remember this notation, rho of x comma y, which is nothing but the covariance of x comma y, that is covariance of these two variables divided by product of standard deviation of the variables x and y. The sigma x is nothing but standard deviation of x series, where sigma y is nothing but standard deviation of y distribution or y series or marginal distribution of y. Okay. Now, in this topics, normally you get a problems. Okay, only on these things, namely, first one is forming or finding the joint product distribution. So that is by forming joint probability contingency table, where you'll be given two variables x and y. Okay, and a random experiment. In fact, you are given a random experiment in the first sentence, then two variables are defined that, and you asked to find out the joint product distribution corresponding to those two discrete variables. First kind of problem. Second kind of problem, you will be given a joint probability distribution. From that, you are asked to find out marginal distribution, and you may also check whether the variables are independent or not. And also, in addition, in another kind of problem, you may be asked to you may be given marginal distributions where the variables are independent, and you may also find out joint probability distribution. Okay, and in other kind, so you may also find out covariance of x comma y. There's two variables of a joint product distribution, and correlation coefficient rho of x comma y. These are the problems you come across on these topics. We take up the problems one by one in the next video. Okay.